Hello everyone, welcome to our differential equation class. In this video, we continue studying applications of the linearization analysis to find qualitative solutions of nonlinear systems. The system we are going to study today is the pendulum, and we are going to study the solutions of the equation for the pendulum in the case of both small oscillations and large oscillations. The later case, large oscillations, is called the nonlinear pendulum. The equation that describes the pendulum is Newton's equation of motion, which is a second-order equation. And to do our linearization analysis, we need to write the second-order equations as a first-order system, and then we can carry out the linearization analysis. And we are going to have three main cases: the case where we have no friction, small friction, and large friction on the pendulum. So that's the plan for today. Let's start introducing the equations for the nonlinear pendulum. And the pendulum is a system given in this picture where we have a mass, an object of mass m, that is attached to one end of a rigid cord or a stick of length L, and that stick is attached to a pivot that can oscillate freely without friction. So then the movement of this object of mass m is going to be on a circle of radius L. Has to move on that circle because this stick is a rigid stick, and we assume is massless. All the mass is concentrated in the object at the end. So the pendulum is going to move back and forth on the circle, and the main variable to describe that movement is the angle with respect, in this case, to the vertical line. And we have to introduce some conventions for the angle. And we are going to say when the angle is on this side of the vertical line, the angle theta is going to be positive, and when we are on this side, it's going to be negative. Here, the angle is going to be 0, so let's say that theta is going to be, oops, that is not good. Theta is going to be 0 here when the mass is there, and when the mass is here, then theta is going to be pi. So this is what we say over here. But there is a complication. Theta could be 0 when the mass is here, is 0. So we are here. But it could be also, it could be in the same position if it does a one complete turn and is 2 pi. So this position also represents the position of the pendulum after 2 pi or after a second turn, which should be 4 pi, and so on. And actually, this position here represents the position of the pendulum even if it moves from the other direction, and in that case it's going to be negative 2 pi, and then one more turn, negative 4 pi, and so on with many turns. So the position here of the pendulum could be theta equals 0, or theta equal 2 pi, 4 pi's, and so on, or negative 2 pi, negative 4 pi, and so on. The same happens here when the pendulum is all the way up. This could be pi, this is pi, or it could be 3 pi, and so on one direction or the other. So it could be, the position could be pi, or 3 pi, or 5 pi, or negative pi if it came from this side. Now it's negative pi, negative 3 pi if that's one more turn, and so on. So that is one little problem that we have with the pendulum, that if we take a picture of the pendulum, we don't know what is the angle. We know the angle only except multiples of 2 pi. Okay, the distance that the pendulum, the object of mass m move depends on the angle theta, and the length of the rod is, of the stick, is L times theta. Recall theta is going to be a function of time pretty soon, but L is a constant. And what are the forces that we have on the object of mass m? Well, on the object we have the force of gravity, and now the gravity points downwards, and we need a coordinate system to write that vector. So we are going to use little vectors here to draw the direction. This vector here, we are going to call it vector k, that points up, and the vector j is going to be here unit vectors. These are unit vectors. J, here is 1, here is 1. Using these little vectors, unit vectors, then we can write that the force of gravity acting on the object of mass m, because it's pointing downwards and k points upward, is negative that vector k. The mass times the acceleration of gravity. The acceleration of gravity is around 10 meters per second squared. What else do we need? Well, this is a rigid stick or a rigid string, so it doesn't change the length. So that is what allows the movement to be on a circle, and that means that a part of this force due to the weight is cancelled by the stick, that part. So in order to do that, what we should do, in order to compute what is that, we should decompose the weight, the force of the weight, in two directions. In the directions along the stick, that part of the force we don't care, because it's going to be cancelled automatically by the rod. So the only part of the weight that creates the movement is the tangential part. Is the tangential part, which is this part here, and that is the only force that creates the movement in the case we don't have friction. In the case we have friction, then there's more forces, but without friction, this is the only force, and we need to compute that force, and we use a little bit of trigonometry to do that, because this angle here is again theta. So then this force over here is the weight of the force due to the weight, m times g, and then sine. This is going to be the sine of the angle theta. And now in which direction? Well, it's in this direction, but it's hard to write in terms of k and j. So we are going to introduce other vectors that are going to be unit vectors along the tangent of the circle where the pendulum moves. Let's call it the tangent vector, tau, unit vector. And then the radial vector. Here, this is the radial vector. We are going to call it rho, Greek letters for radial and tangent. And then here what we have is, well, and we are saying positive is in that direction because it's the direction where theta increases. So when the velocity is positive, it is going to mean that we are moving in that direction. So this is the direction of the tangent vector we chose, in the direction of positive velocity. So here we need to multiply by tau, because this is a force that is tangent to the circle, and in the opposite direction of the vector t, because the weight points downwards. So this is the force due to gravity that creates the movement on the pendulum. I have it here written in a little bit nicer on the other side, and actually with one more ingredient. So this is what I try to write. These are the vectors jk. These are the vectors tau rho. This is the component of the force. This force is cancelled by the stick, so we don't care. And this is the force that is creating the movement, which is the force due to gravity, the tangential part. And I draw here one more force, and that force is the force due to friction with the air, for example, or maybe the pendulum is oscillating in liquid or in oil. So we are going to have a force due to friction, and that force is proportional with a proportionality constant d that is 0 when there is no friction, or positive, is called the damping constant. exactly in the same way that we did to describe the motion of the spring in a medium with the damping constant. So and the force is in the opposite direction of the velocity. So there is a constant and the velocity. So this is the velocity. Well, actually, this is the velocity. So to draw the force, I need to know the velocity. And recall that if we have only the picture here of the pendulum, we don't know what the velocity is because this is just a picture. We need to give that information on top of the picture, because this pendulum could be moving with velocity in that direction or with velocity in that direction. And the force depends on in which direction it's moving, because the force due to friction always opposes the velocity. So if I draw the force in this direction, that means I am assuming that the velocity of the pendulum in this case is going in that direction. So the velocity is negative in this case, and because of that, then the force has to be positive. So this velocity is negative, these negative signs cancel out, and then the force should be in the direction of the tangential vector, and that's why I draw it in that direction. So to draw the damping force, you need to know more than a picture. You need to know in which direction the pendulum is moving, because that force is opposite to the velocity. To draw it in this direction, I was assuming the pendulum was going down now. If the pendulum was going up, the force should be in that direction if the pendulum is going up. So this is the system with all the forces. And now we need to use these pictures to actually write down the equations of motion. And I have them here. The equation of motion is Newton's equations in the tangential direction, because there is no motion in this direction. So Newton's equations only in that direction, in the tangential direction. And if we look at the equations, well, let's remember Newton's equation. Mass times acceleration, recall this is only tangential direction, is equal all the forces acting on the pendulum. And the forces acting on the pendulum are, well, we have two forces, the green and the blue. The green and the blue. And these forces, we call it the force of gravity in the tangential direction, plus the force due to friction that is always in the tangential direction. Recall that what we have over there, that the force due to the tangential direction on the gravity, why I'm doing red? Let's keep it blue because this force is written in blue here. That force is what we wrote over there. It's all in the tangential direction, so I don't need to write already this vector. So I'm just writing down the sign and the magnitude, which is mg sine of theta. And then we have the force in green, that is the force due to the friction, and that is always in the opposite direction of the velocity, which recall we have it here. The motion along the circle is a constant times the angle theta. So this is the same as negative d, then the length constant, and then theta prime, because theta is a function of time. And also here, theta, let's write it down here, theta is of course a function of time. All right, then all that, and recall what was the acceleration here. The expression for the acceleration is the second derivative of the position along the circle, and this is gonna be equal L times theta of t double prime, and this happens to be L theta double prime. Okay, a little bit too close for my taste, so let's put a line here to separate these two calculations. And now recall, well, we use that L is constant and theta is a function of time. And then we have the and then we have the equation of motion. If we put everything together, we are going to have, let's put it here, mass times acceleration. Recall the acceleration is L times theta double prime is equal all the forces, but we have two forces, the force minus mg sine of theta, recall is a function of time, minus dl theta prime. So we usually divide by m and l, and we get the final expression for the equation, which is going to be theta double prime is going to be equal, when we divide by m, this m is cancelled and we have g over l. We divide by L2 sine of theta minus L is cancelled out and we get d over m, and then we have theta prime. And this is the equation for the pendulum that you see is a non-linear equation. This equation is a second order, first of all, second order, but is non-linear because of the sine of theta. That makes it non-linear differential equation. So, and in the unknown is the function theta as function of time. So this is the equation for the nonlinear pendulum. Let's see what happens to this equation in the case of small oscillations. Small oscillation means the pendulum here is moving only from, let's say, this position to that position. So the theta for all times is much smaller than 1 radian. 1 radian is like here, so 10 times smaller at least. So this is what we call the small oscillation approximation. What happens in that case to the equation? Okay, so we have theta. We are saying theta is for all time is going to be much less than 1. And then what we can do is we can do the Taylor approximation of the function sine of theta for theta small, and this is going to be approximately equal theta. This is Taylor approximation, the first term in the Taylor approximation. So the equation now, it looks like theta double prime is equal negative g over L, and then what do we have? Multiplied by theta now, minus d over m multiplied by theta prime. Okay, let's multiply by m, and let's put everything on the right hand side, and then we are going to have an equation that is going to look like mass times theta double prime plus d times theta prime plus mg over L times theta equals 0. So we obtain these equations for small approximations, for small oscillations, sorry. So, well, this equation, it should be familiar to us because it's essentially the same equation as the equation that describes the movement of a spring with constant k and an object attached of mass m oscillating in a medium with a friction coefficient d. And this is our coordinate system. And if we write down the equation in this case, recall it has the form mass times y double prime plus the friction coefficient times the velocity plus the constant k, y equals 0. And you can see the name of the constants is here is different, but other than that is exactly, well, is the same equation. So what this says is that these two equations are mathematically equivalent. So the motion of the pendulum with small oscillation is exactly the same as the motion of a mass spring system. For example, we know that for the mass spring system, when we have, for example, no friction, then the oscillation, the frequency of the oscillation is k over m square root. Well, the same happens in the other system. When we don't have any friction, then the movement is gonna, the pendulum is gonna move with a frequency of oscillation that now is gonna be g over L square root. So what we see here is the larger is the length of the pendulum L, the smaller is the frequency, which is the smaller is the frequency of oscillation, which you can try at home, or you have seen it in many cases. The longer the stick in the pendulum, the smaller the frequency of oscillation. So this is the small approximation of the pendulum, is just the movement of a mass spring system. So in summary, for small oscillations, a pendulum oscillates like a mass spring system. So now let's move on to a first order reduction of the equation of the pendulum, because recall what we want to do is we want to sketch an approximate phase portrait of the solution of the equation for the nonlinear pendulum. But the equation for the nonlinear pendulum is right now is not a first order system, it's a second order nonlinear equation. So we need to write the second order equation as a first order system. So we need to write this equation, equation 1, as a first order system, and after we do that, we can study the phase portrait of the solutions. Okay, so how we do that? Solution. Well, this is first order reductions, is simple. We do it in the same way we have been doing all these first order reductions. We introduce the variable x1, which is going to be the original variable, theta. This is actually the angular position of the pendulum. And then we introduce x2 of t, which is the derivative of the previous variable. So theta prime, which now has physical meaning, is the angular velocity. Okay, with these two variables, with that definition, we always have one equation for the new variables, which is x1 prime is obviously x2. Okay, we got that first equation for the system, which is always like that with these variables. What is the second equation? The second equation is the equation for x2, which the derivative of x2 is now obviously theta double prime, but now this is equal negative g over L. Then we have sine of theta minus d over L theta prime. But we just said that theta is x1, so we have negative g over L, that is an L sine of x1, and then minus d over L, d over m, sorry, mistake here and mistake here. The equation says d over m, and here is x2. Alright, so that is the second equation. So if we put both together in a nice way, we are going to get x1 prime is actually equal x2, and x2 prime is now negative g over L sine of x1 minus d over m x2. And that's the equation. So the system of first order nonlinear differential equations. So this is a first order system, which is nonlinear because of the sign, differential equation. Okay, so this is the system we need to study. Well, it has a few constants, so g over L and d over m. So for simplicity, what we are going to do is we are going to take a particular case where G over L is 1, so we don't have to write this constant all the time, and the mass is 1, but we are going to keep this friction coefficient arbitrary because the movement is very different for different values of this friction constant. So our system, the system we are going to study, is this. So with the 1 here, so to write simple equation, and with the coefficient D. Now that we have the system of equations that describe the nonlinear pendulum, we can start our linearization analysis. And the linearization analysis is to sketch an approximate first portrait of solutions to the nonlinear pendulum equations, which are these equations. Recall, we have these equations because we are in the particular case given by these two conditions to simplify the calculations. Okay, so how do we do the analysis, the linearization analysis? Like we always have done in the previous videos, we start computing first what is the vector field of the equation. So vector field. Well, the vector field is the right-hand side of on the system of equations. So f function of the point x on the phase space is going to be x2, and then here we are going to have minus sine x1 and then minus d x2. So this is a vector, and recall we are using the convention for x that is, as always, x1 and x2, but because this is a first order reduction, x then has the angular position and the angular velocity as components. Okay, so now what we do is we compute the critical points. Critical points, which, as we know, are all the points where the vector field vanishes. So let's write that down here. Is the points, let's call it x0s, where the vector field vanishes. Okay, so what is that? That gives us x2 equals 0 and minus sine of x1 minus dx2 equals 0. And because x2 is 0, then the second equation says, oh, then sine of x1 has to be 0. And the solutions are x1 multiple of pi, any multiple of pi. Here n can be 0, can be plus or minus 1, can be plus or minus 2, so on. So we end up with infinity many critical points, and the critical points can be labeled with the index n and an integer, and these are x1 has to be multiple n times pi, and x2 always has to be 0. So these are the critical points. This is new with respect to previous videos in the sense that now we have infinity many critical points. We can see them if we go to the phase space. The phase space, recall, is the space x2, x1, which in this case is theta prime, and then we have 0, pi, 2 pi, negative 2 pi, and so on, infinity many. But they are all on the horizontal line x1, the angular position theta. What are these little things here? This is just to remind us that the phase space, what is the relation between the phase space and the physical space? In the physical space, if we are moving in this region from 0 to pi, we are here, in this region right there. But recall the position here is not unique in the sense that, oh, maybe we were here because we did one full turn and now we are here, so that means we could be here. In the phase space, we have no way to distinguish with only this picture if we are here, or if we are here, or 2 more pi over there, or 2 more pi over there, or if we arrive to this position by going in the opposite direction, so here. And the same if we are on this region, we could be here or a multiple of 2 pi or a multiple of 2 pi. So the physical space, this picture cannot characterize the motion of the system, in the sense we don't know in which multiple of pi we are right now. The phase space gives you that information, because if we are here, is because we didn't do any multiple of pi rotations, but if we did, we are going to be here. So the phase space has more information than this picture on the physical space. Also here is a picture, we don't know if the pendulum is moving up or is moving down. We have no information about the velocity in this picture. Here in the phase space we do, because one of the axes is the velocity. So if the pendulum is moving up and is in the first, the angle is actually smaller than 2 pi, then we are here, and actually positive velocity, we are right there. If it's moving in that direction, we are here. If it's moving in negative direction, but it did 2 turns, then we are here. If it's moving in positive velocity, but it did 2 turns, one, and then positive velocity, then we are here. So a position in the phase space determines exactly the position with multiple of 2 pi's where the pendulum is, and also the velocity. Here, not. So physical space, that picture gives us less information than the phase space. Alright, enough of that. Hopefully we understand what it means, a point in the phase space. And now let's keep working with the linearization method, and let's compute the derivative matrix and its linearization, which now they are infinity many. Recall the field, the vector field copy is given by that expression, and we usually write that vector field as f1, f2, and with that notation we introduce the derivative matrix, function of the point, of course, which is the derivative with respect to x1 of f1, derivative with respect to x2 of the same f1, then derivative with respect to x1 of f2, and derivative with respect to x2 of f2. If we do this calculation, it's pretty fast in the pendulum, and the calculation gives us the following derivative matrix. We are going to have 0 in the first component, 1, then the derivative of the sign, which is going to be cosine, and there is a negative sign, so negative cosine of x1, the other term disappears, and then the derivative with respect to x2 is negative d. And that's it. That is the derivative matrix, pretty easy to compute. Recall, we are going to study the case d bigger or equal 0. And recall, we have also critical points. The critical points are what are the critical points? X, n, which are n pi 0. And that means that the derivative matrix on those critical points is going to be, well, of course, 0, 1, negative, let's put it here, negative cosine of n pi, and then negative d. But the cosine of n pi is easy to compute. Oh, this is a little bit tilted there, a little bit better. And well, let's recall here. What is the cosine of n pi? Well, it's +1, -1, +1, -1, depending on n, so it's -1 to the power n, actually. And then, let's move this, it's too close. Then, what do we end up with? We end up with d the derivative metric at the point xn is going to be 0, 1, negative 1 to the power n, and recall there was another negative 1. Let's move this a little, let's move this a little bit to the right, alright, and then negative d. Alright, but let's write it down in a slightly better way. The derivative matrix, this is our final expression for the derivative matrix, is going to be 0, 1, negative 1 to the power n plus 1, because there was an extra negative sign here that add up to 1 power, negative d. That is the derivative matrix. So it's not as complicated as I thought it would be, and we have actually not infinity many cases to compute for the derivative matrix. We have only 2 cases: the case n even and the case n odd. That's all. Because in the case n even, so let's say n equal 2k for any k, what happens? We have that negative 1 to the power n plus 1 is equal negative 1 to the power 2k plus 1, but this is the same as negative 1 to the power 2k times negative 1, but this is the same as negative 1 squared to the power k, isn't it? Times negative 1, but negative 1 squared is 1, so this is 1 to the power k, which is 1, multiplied by negative 1, so this is negative 1. All this calculation to say that this, for n even, this factor doesn't depend on n. On the other side, something similar happens. Negative 1 to the, what is n? N is odd, so it's 2k plus 1. So n plus 1 is negative 1 to the 2k plus 1 plus 1, so plus 2. So this is just negative 1, 2 to the power 2k plus 1. And now we play the same game as before. This is negative 1 squared to the power k plus 1. But this is 1 to the power k plus 1, which is of course 1. So we can have in that coefficient either 1 or negative 1 for the 2 cases. So we arrive to these expressions for the derivative matrix. Either it has a negative 1 in that position for the even critical points, or it has a positive 1. So this is the whole difference is right here. For even critical points we have a negative 1, for odd critical points we have a 1, and then the picture is then that we have 2 types of critical points. The odd critical points, which are we are going to have some behavior there, and then the even critical points, here, we may have a different behavior because of that difference there. To find out what behavior do we have in even and odd critical points, we need to compute the eigenvalues and eigenvectors. So let's start with the eigenvalues. The eigenvalues, well, but we have 2 matrices to work with, this one and this one. Let's start with the even critical points, so this matrix here. So the eigenvalues are the solution of 0 equal the determinant of negative lambda, so matrix minus lambda identity. So we have a 1. Now we are working with this matrix, so we have a negative 1 right there. So negative 1 and negative d, negative lambda. That determinant. And that determinant is equal to d plus lambda multiplied by lambda. I cancelled the 2 negative signs. Minus minus plus 1. And if we compute that, this is lambda squared plus d times lambda plus 1. And if we compute the roots, lambda plus minus, this is 1/2, and then we have minus d plus minus the square root of d squared minus 4 times 1, so 2 squared. Okay. And if we do the other case, the odd critical points, well, we need to change, the whole calculation is the same, we need to change this -1 into +1. So let's do that. Let's copy everything, because it's gonna be the same, except copy. One little calculation, so now the only difference is we don't have these -1s, we have a positive one, so this product is the same, and then we have -1. Okay, -1. So it's gonna be a -1 there. And then the eigenvalues for this case are gonna be 1/2. We still have a -d plus minus the square root of d squared minus minus plus 4, so plus 2 squared. So you see that's the only difference. This negative sign becomes plus sign because of this negative and this positive. All right. But here, in this case, we have that we always have real roots. So this is always real roots. But here is not, depend on d. If d is 0, the roots are, and 0 here, the roots are pure imaginary. If d is smaller than 2, this is negative, and the roots are complex. And if d is bigger than 2, this term wins over that, then the roots are actually real. So depending the relation between d and 2, the number 2, we have different behaviors for the solutions of the nonlinear pendulum. So that leads us to the following friction cases. D equals 0, we have no friction, and then the solutions are going to be eigenvalues with pure imaginary roots, which means oscillations without decay. We know that from studying linear systems. When d is between 0 and 2 is what we call small friction. So this term is now negative, but is still different from 0. So we have complex roots for the eigenvalues, complex eigenvalues. And that means oscillation with decay, because we are going to have a decay given by that coefficient there, which is negative. Oscillations with decay. When the friction is bigger than or equal to, we call it large friction, and now we have decay without oscillations, because this is positive, we have real roots. One question we could ask right now is why 2 appears here? What 2 has to do with physics here? Why friction has to be less than 2? This looks like an universal property of the pendulum, but it's not. It's nothing universal, it's actually the opposite of universal. 2 appears here because it appears here. And the reason we have a 2 there is because we chose a simple case where G over L is 1 and the mass is 1. Otherwise, G over L should be here and mass should be here. And actually, if you keep G and L and M arbitrary, this condition is replaced by, so this, for example, this condition here is replaced by this condition here. You see, when G over L is 1, you have a 1 here, M is 1, and the 2 we put it on the other side, and this 2 is the 2 we are seeing here. But actually this is the condition for, this is the case, small friction, isn't it? Small friction. And the condition of large friction is, of course, d over 2 over m bigger or equal the square root of G over L. Recall the square root of G over L, that is the frequency of oscillation when there is no friction, but that frequency changes with friction. And this is the case anyway, large friction. So 2 is has nothing special. It's actually a product or the result. Oh, this is like this. Is the result of having chosen this particular case to simplify the calculations. Otherwise, we should get these conditions. Okay, let's go back to our case. The G over L equal 1 and M equal 2, and then everything has to do with 2. So let's study the case no friction first. So we are going to go in detail on this case, and then we show what happens in the other two cases. In this case, what we need to do is we need to compute the well, in this case we already mentioned the derivative matrix in the case where we have even critical points, so x, 2k, these are even critical points. Recall the matrix when we have no friction. We were working with this matrix, isn't it? But now we have no friction, so we have a big 0 here now. So it's 0, 1, negative 1, 0 now, because we are in this case now. So we have 0, 1, negative 1, 0, no friction. Okay, and in the it's kind of too close here. There. And then this is for even critical point. What happens for the other case, for derivative matrix on odd critical points, 2k plus 1? Well, it's the same here, 0, 1. Then we have positive 1 and 0 because we have no friction. So in this case, we have even critical point. And here we have odd critical points. What happened with the eigenvalues? Well, we computed the eigenvalues up there. Eigenvalues. Well, the eigenvalues, if you recall, we are here. We are in the even critical points. This is 0. This is 0. Plus minus 2i divided by 2, so plus minus I. So we have here lambda plus equal I, lambda minus equal negative I. Let's draw a line because it's getting too close. What happens in the other case, in the odd? Well, in the odd, which is here, we have d equals 0. D equals 0 is plus minus 2 divided by 2, so plus minus 1. They are real in this case. So let's copy this over here. Copy, paste. What are the eigenvalues in this case? Well, plus and minus 1. Lambda plus is equal 1. Lambda minus is equal negative 1. Real. What happened with the eigenvectors? Well, if you compute the eigenvectors here, I'm not going to do it, but the calculation, but the result is negative I, 1 for lambda for v plus, and v minus is the conjugate, so I, 1. Okay, a little bit too close also. Maybe we can move everything a little bit here, there. And what happens for the eigenvectors in the other case? Copy, paste. You can do the calculations, but here I'm showing you the result. V plus, in this case, odd critical points is going to be 1, 1. And V minus has to be computed, and it's going to be negative 1, 1. So we see here that for the even critical points, we are going to have centers, which is about a notice, centers. And here we are going to have saddles. Saddle nodes. All right, now the problem, we have a problem with the centers, because our main theorem, the Hartman-Gromman theorem, does not give us any information about the nonlinear system if the linearization has centers. The linearization has centers, then we need no Hartman-Gromman theorem that we can apply. So we need further study, for example, study the direction fields, And if you do that, you're gonna see that the nonlinear system also, in this case, also behaves as centers. So the fact that the linearization is centers doesn't say anything about the nonlinear system, but further study reveals, yes, they are centers too. And here, for the saddle nodes, the Hartman-Gromman theorem says, oh, the nonlinear system is going to behave like saddles. So with all that, we conclude that this is the behavior of the solution of the nonlinear pendulum near the equilibrium solution, the critical points, for even and odd critical points. We have saddles for odd critical points. We have saddles with these eigenvectors give you this picture, and then you have the centers, and the centers are rotating in this direction. Why they are rotating in that direction? Why I did the picture like that? Well, that comes from the eigenvectors we got. Recall that we have an eigenvectors v plus, which are negative I1. Well, recall this is just 0 plus negative 1 multiplied by I. This is 1 plus 0 multiplied by I, which means that this is the vector 0, 1 plus the vector negative 1, 0 multiplied by I, and that means that this vector here is what we usually call the vector A. This is what we usually call the vector B. So all this give us that the vector A is 0, 1, which actually is a vertical vector pointing up, and then B is the vector negative 1, 0, which is a horizontal vector but pointing to the left. And with that, recall the rotation is always in the direction A to negative B. And this is B, this is A. I draw it too long, but I should have drawn it like a circle. Well, let's do it then, because I don't know why I did it so long. Let's change that into something like this, and then let's see if we can change this ellipse into more like a circle. There. Okay, and now these vectors are outside. Okay, so this is what we get, and now the direction of rotation is in the direction A, negative B. The negative B is let's put it here. There. So this is the ground color. This is the direction of rotation. So I have to rotate in that. It's fixed by the problem. Okay. And that gives us, because of the relative position of A and B, that gives us clockwise. So we end up with this picture now. We end up with this little picture, where we have the little oscillations, small oscillations. They are going all in that direction. And then we have some other curves we are going to discuss in a minute. But let's understand these little oscillations first. Why I call them little oscillation, and what is this curve here, and what is this curve here that they are drawn in different colors. And that should be information for later. So to understand what these little curves are doing, I have here some pictures that, well, GIFs that I found, I stole from Wikipedia. And this is what happens when we have a small oscillation like this one here. The pendulum is oscillating back and forth, and you see when the pendulum is moving in this direction, we are in the lower part. When the pendulum is moving in that direction, the velocity is positive and we are on the other part, and very small. Bigger oscillation means a larger curve, but there are no circles anymore. You see the frequency now is it changes with the position. And you see here, the more the larger oscillation is way different from a mass spring system. Here, the movement of the pendulum is like a mass spring system, but not here. The mass spring system is circles or ellipses. This is not an ellipse anymore. Neither this, neither that. And this is what we mean by that. And notice that this picture is, the pendulum is almost stopping. So let's go, it goes all the way, it's almost stopping here, but it comes back. This curve over here, the curve in purple, is just one solution when the pendulum actually goes from let's see, from here, and actually stops at the top. That is that curve stops at the top, never reaches the top, but it gets in infinite time. The top is one solution. When the pendulum is here, it doesn't move. It's an unstable solution, but it doesn't move. It's that point here. When the pendulum reaches this position from the other side and doesn't move, that is this solution. These are the equilibrium solutions which are unstable. So when the pendulum reaches the top in infinite time is this solution. When the pendulum reaches the top on the other side is this solution. So this is one solution, this is another solution. And then this is one solution when the pendulum is oscillating. Here there are no oscillation. It goes to the top and stops. It goes to the top and stops. And then what happens when we have more velocity than that and we are here? Well, then the pendulum does something like this. And what is that? That is when the pendulum goes over the top. Forever. And these are these curves. Goes over the top in one direction, goes over the top in the other direction. So this is the picture, the phase portrait of the pendulum for friction coefficient equals 0. And here we have very few solutions. We can add more solutions, and then the result is going to be something like it's going to be what is that? That is nothing. It's going to be something. So the conclusion for the case no friction is this. With all the solutions, recall this is just one solution, this is another solution, then this is one solution, and these are the open over the top solutions with more and more velocity, and then everything in the other direction. And here are the critical points. So that's the movement of the pendulum with no friction. What happens when we add friction? Well, when we add friction and the friction is small, then the only change in this solution is that the centers become sink spirals. And here it is. What happens? Everything is the same, but now the motion of the pendulum, for example, this is going over the top, and then at some point it loses velocity and start oscillating and go to the center. And that movement is essentially, we have the pendulum, it goes over the top 1 or 2 times, and then it starts oscillating back and forth, and stops. When the solution reaches in infinite time the equilibrium solution, it stops. And that happens on every critical point. At some point it's going to stop. And what happens when we have large friction? Oops. Well, something similar but without oscillations. So the pendulum is going over the top, and then at some point stops. So the pendulum here goes over the top, and then the next time it stops here. And that's all it does, because there is so much friction. So here it is. The equation for the nonlinear pendulum provides this phase portrait for the solutions in the case of no friction, small or large friction. That's all for today. See you guys in the next video.